My pleasure to introduce Professor Carolina Araujo, and she is from IMPA, and she will give a talk on special subgroups of the Cremona group via Calabi-Yau pairs. Thank you, Carol.
Thank you. First of all, I would like to thank the organizers for the invitation. And today I would like to report on some recent results that I have been working on with Alessio Corti and Alex Massarente, where we produce some special subgroups of the Cremona group via Calabi-Yau pairs. So I will explain all these terms, but let me just say that Calabi-Yau pairs are objects that appear in higher dimensional algebraic geometry in the context of the minimal model program. So let me start first by recalling what is the Cremona group. So the Cremona group in dimension n is the group of birational self-maps of Pn. So these are just rational maps from Pn which have inverses as rational maps. So these are birational. And so this is, so this includes, for instance, so examples of birational maps. Of course, this include the automorphism group of Pn, and these are sort of, we consider them boring from the point of view of birational geometry. But there are some more interesting elements. So the simplest one in dimension 2 is the standard quadratic transformation. So this is just the, let me call it Q from P2 to P2 that takes the form. So I think the easiest way to write this down is 1 over x, 1 over y, and 1 over z. But if you want to write it with polynomials, so this is the same thing in projective coordinates of writing yz, xz, xy. So from this description, it's very easy to see that that q square is the identity. So this is an evolution, but this is not, it's really a true birational map. It's not defined exactly at the coordinate points. So the geometry of this map is the following. So it is not defined at the coordinate points. And it takes, if you look at the coordinate lines, they are contracted to the coordinate points. And outside these three lines, this is just an isomorphism. So this is what we call the standard Cremona transformation, or the standard quadratic transformation. So this is the first non-trivial element of the Cremona group in dimension 3. But in dimension 3, we actually know more. So in dimension 3, there is this classical theorem by Neder-Castelnuovo, so this dates back to the 19th century. So Neder first stated it in 1870. The proof was slightly incorrect, and it was completed by Castelnuovo in 1901. So what they prove is that these elements are enough to generate the whole Cremona group in dimension 2. So they prove that the birational, the Cremona group of P2 is generated by the automorphisms. So this is just PGL3. And this standard quadratic transformation. So this is a very simple description. And it may make you think that we know everything we want about the Cremona group, but this is actually far away from being true. So there are still many aspects of the Cremona group that are still unknown, and this is a very active area of research in birational geometry. Let me just mention two results that were obtained only 10 years ago. So one of them, some remarks. about the Cremona group in dimension 2. So only recently the classification of finite subgroups was completed. So classification of finite subgroups of the Cremona group in dimension 2. So this was this started with work of Bertini again in the 19th century, and had contributions from Cantor, Castelnuovo, Segre, Manin, and it was finally finished in 2009 by Dolgachev and Skovsky. So this is a classification of the finite subgroups. And something that may look even more surprising is that only 10 years ago, it was proved that the Cremona group is not simple. So the Cremona group of P2 is not simple. And the construction of the first normal subgroup was done in 2000 and 2010 by Cantat and Lamy, and since then there have been a lot of work to construct new normal subgroups of the Cremona group. So this is in dimension 2. So you can imagine that in higher dimension things are even more complicated, and it's true that in higher dimensions, so for n at least 3, the Cremona group is wild. It's very mysterious. We know very little. So for instance, let me just state a theorem by Hilda Hudson from 1927. So she proved that in dimension at least 3, the Cremona group cannot be generated by elements of bounded degree. So this is very different from the case of dimension 2, where the group is completely generated by automorphisms, which are maps of degree 1, linear maps, and this quadratic transformation, which has degree 2. So in higher dimensions, so for n at least 3, the Cremona group in dimension n cannot be generated by elements of bounded degree. And so we don't even have a nice a way to describe the generator. So the structure of this group is completely wildly unknown. So one problem that comes up in higher dimensions, so problem, and this is the problem that we have been addressing, is to construct interesting subgroups of the Cremona group in arbitrary dimension, to construct interesting subgroups of the Cremona group, especially, well, also in dimension 2, but especially in higher dimensions. Okay, so let me give you one example of such special subgroup still in dimension 2. So this was constructed by Blanc in 2013. So he considered the following. In the plane, he considered the meromorphic volume form given by dx over x, wedge dy over y. So this is I view this as a meromorphic volume form, and it has simple poles exactly along the 3 coordinate axes. And he considered this space, the subgroup of the Cremona group, that preserves this volume form. So let me just write it this way. So with this notation, I mean the birational transformations that preserve this form. And so, for instance, it's very easy to see that the standard Cremona transformation that I was discussing, clearly, if you plug in the coordinate functions here, you will see that it preserves this volume form. So in fact, Blanc gave a complete description of this group. So let me just state this. So this is the subgroup generated by SL to Z. The two-dimensional torus, and then one special Cremona transformation. I will write it in a fine form, y1 plus y over x. So this is a transformation of order 5. So when I write the two-dimensional torus here, I really mean you just have two complex numbers and you just multiply x by the first element and then y by the second element of the tuple. And then this group here acts, so here, an element here is a matrix with integer coefficients a, b, c, d, and it will act on x. Let me write again in affine coordinates. It will take xy to xa, yb, xc, yb. So the standard Cremona, standard quadratic transformation is one example when a is -1, b is 0, c is 0, and d is -1. Okay, so we have this special subgroup, and the idea is that we would like to generalize these results to higher dimensions. So we still don't know how to do it, but but what we started to do is to consider different meromorphic forms. So let me just make some remarks about meromorphic forms on P2, meromorphic volume forms on P2. Okay, so here is in P2. So if you have any omega, a meromorphic 2 form in P2, I can consider the divisor associated to this meromorphic form. So this divisor is just the divisor of zeros minus, so the divisor of zeros minus the divisor of poles. So for instance, if I take the form considered by Blanc, it has no zeros, and it has exactly simple poles along these 3 coordinate lines. So this would be, the divisor would be just this minus the sum of these 3 lines. So in general, if I take another volume form, this will give me a different divisor, but it will always be linearly equivalent to minus 3L. So the class, when I write this, what I'm saying is that the class of this divisor inside, you can think of this either in the Picard group of P2, or in this case, the same thing as the cohomology group of, second cohomology group of P2. So these are all generated by the class of the line. So it doesn't matter which meromorphic 2 form you start with, the class of the divisor is always the same. So this is what we call the canonical class of P2. And so we could, instead of looking at this meromorphic form, we could have looked at another other meromorphic forms, and this is what we are going to do. But we are going to do this in higher dimensions. So let me just say that also for now, for n, for arbitrary n, again, if you take a meromorphic n form and you look at the divisor associated to it, it will always define the same element in the Picard group or in the cohomology group, which we denote by KPN. And this is going to be the class of minus n minus 1 times a hyperplane section inside, say, the Picard group of Pn, or the cohomology group. So these are the same in this case. And so what we are going to do now is to start with different meromorphic forms and consider the subgroup of the Cremona group that preserves this meromorphic form. So let me just add the remark that if I start with any D in Pn hypersurface of degree n plus 1, so for every hypersurface, I can cook up a meromorphic form omega d such that the divisor of omega d is precisely minus d. So it does not have zeros along hypersurfaces, and all the poles are along d. Okay, so now what we want to do is if we fix a top meromorphic differential form, or in other words, if we fix the hypersurface, what is the subgroup of the Cremona group that fixes this, preserves this meromorphic form? So the problem that we want to address now is this, so problem. If we start with D in Pn, a hypersurface of degree n plus 1, we want to describe the subgroup of the Cremona group of Pn that preserves this meromorphic form. So that by that I mean that if you plug in, if you have the equation, you know, the coordinate functions of your Cremona map, you substitute it in the form, and you want to get the form itself. So this, by simplicity, I will just denote this by the group, the special Cremona group. Now here I will just write D instead of writing omega D. Okay, so this is the problem, and let me now state the two theorems that we can prove at this moment. So the first theorem, so let me say theorem 1, or theorem A, says the following. So eventually we would like to use this nice symmetric meromorphic form in higher dimensions, but this is very degenerate. You know, this in a sense, if you look at all hypersurfaces of degree 3, this is a very degenerate one. And so let's start with the simplest one. You know, if you start, for instance, with a very general hypersurface of degree n plus 1. So if the first theorem that we prove is that so here n is at least 3. It's interesting that something different happens in n for n equals 2, but for n at least 3, then what we prove is that if D is general, or maybe here I should even say very general, but this is okay, then this group is not really interesting. So then the group of birational maps of Pn that preserve the form associated to D is just the group of automorphisms of Pn that fix the D. So this is not very interesting, but and then we start. Let's look at the next case. So the next case. So here in dimension, so in dimension 3, what is the first singular case? So let's start with a D, a general singular quartic hypersurface in P3. So let me write actually the equation of such quartic hypersurface. So here I will use projective coordinates x0, x1, x2, and x3. And I can, after change of coordinates, I may assume that the surface has one singular point at 1, 0, 0, 0. So this will be a singular point of D, the unique singular point. So this is the first degenerate case. So the equation of such D can be written in the following form. So x0 square a2 of x1, x2, x3 plus x0 b3 plus c4 equals 0. So by that I mean that A, B, and C are homogeneous polynomials in x1, x2, and x3 of degrees 2, 3, and 4. So if the surface is general enough, then this polynomial here is going to be irreducible. And what that means is that the type of the singularity, so P, the type of singularity of these, so this is a singularity of type A1. So locally analytic, this is just, it looks like the vertex of a quadric cone. And in this case here, we already get some interesting birational maps that are not isomorphism. So let me just write this example here. So have a map from P3 to P3 that takes x1, x2, x3 to, so let me get this right. So minus ax0 minus b, ax1, ax2, ax3. So I hope you believe me if I tell you that this rational map does preserve this divisor D, or the form associated to D. And you can see that this is not an isomorphism of P3. So it is not, it contracts, for instance, the cone A equals 0 is contracted to the point 1, 0, 0, 0. And it is not defined at the intersection of the hypersurfaces defined by A and B. So this is a non-trivial birational map that preserves this D. And you can check also that it is an involution. And so it generates a group isomorphic to Z mod 2Z inside the group of birational maps of P3 preserving the hypersurface D, or the form associated to the hypersurface.
What does it mean precisely that birational melting preserves hypersurface?
So, okay, so you can think of this in two different ways. You could think of this as birational maps that restrict to a birational map of D. So this is a very geometric way of viewing this. Or you can also view this as saying that if you have a birational map F, say from P3 to P3, it will induce an isomorphism between the two forms of, say, the function, let me write this as the function field of P3 over C. So this is the space of meromorphic birational maps in P3. So you get an identification of these spaces. And one way to define what we call volume-preserving birational map is that the form associated to D here is taken to be a form associated to D. So this is in terms of forms, but it turns out that these two things are equivalent. Sorry? No, so this is, I'm thinking of this as the, yes, sorry, this is, for P3 would be 3 variables. Let me just write this as KP3, function field of P3. So you can view it in this way, or you can view it as it takes D to D. In this case, because the D is very simple, these 2 points of view are the same. It's not true in general, but here it is the same. Okay, so we have this map here that already gives us something non-trivial in the Cremona, the group of volume-preserving maps of P3. And what we prove, so let me write theorem B. We give a complete description of the subgroup of the Cremona group that preserves the D in this special case. So I could actually write down, so in this case here, let me write it this here. So in this case, we have that the group of birational transformations of P3 that fix D, or that preserve the volume form associated to D. It's a semi-direct product of a group G, which I will describe, and this cyclic group. So this is exactly the group generated by this special element. And this G here, well, we actually can write down what are all the elements of G in a form similar or more complicated, but similar to this one. But let me just give a sort of a description of this as a form. So this is a form of GM over CXY. And here it is really 2 variables. So what does this mean? So this means that this is an algebraic group that is defined over this field with the property that if I consider the algebraic closure of this group, of this field, then this group becomes GM. But as I said, I can actually give you a precise description of all the elements in G. But I think I prefer not to do so. Okay, so now let me tell you what are the tools that we use to prove these 2 theorems. So the methods that we use, they actually come from the minimal model program, which we usually abbreviate by MMP. So what is the minimal model program? So the minimal model program is it's a classification program in higher dimension algebraic geometry, which does the following. So the input to this program is let's say, a smooth projective variety X. And then the program gives you an algorithm to perform a bunch of birational transformations on X. And then in the end, the output can be 2 different things. So either, so let's say the first possible output is another variety X, birational to X, such that the canonical class is greater or equal than 0. So by that, I mean that if I intersect Kx with a curve, then it gives me a non-negative number. So this is called a minimal model. Or the second case, we would like to say that the canonical class is negative, but actually what the output is a little bit more involved. What the output gives you is a fibration from x prime to y prime, for which the fiber, the general fiber, so we want to say that this map has relative Picard number 1. You can think of this, it's not exactly the same, but for today you can think of this that the Picard group of F is cyclic and the canonical class of F is negative. So this is, for instance, as we saw, is the case of Pn. Okay, so the next step, so if you, so this program, this algorithm involves many choices. And if you make different choices, you may get to different outputs. But the type of the output, 1 or 2, depends only on x. It's something intrinsic. And then the next question is, okay, so if I make different choices and I get to different minimal models, or in this case, we call this Mori fiber spaces. So these are Mori fiber spaces. So if we get, for instance, to different minimal models, how are they related? Or if you are in the case of where you get to a Mori fiber space, how different possible outcomes can be related. And the answer is very different in these 2 cases. So for instance, for n equals to 2, the minimal models are always unique. So what does that mean? That means that if you fix the birational class of a surface, then there is a unique, well, if there is a minimal model, so if you are in this case, there is a unique minimal model in that class. While if you are, for instance, in the case of P2, then the Mori fiber spaces there can be infinitely many Mori fiber spaces in the same birational class. So Mori fiber spaces are not unique. For instance, if you look at P2, P2 is an example of a Mori fiber space. It's fibered over a point. It has Picard number 1, and the anticanonical class is ample. The canonical class is minus 3L. But you also have all the Hirzebruch surfaces that are fibered over P1. So these are P1 bundles over P1. And what distinguishes one Fm from another Fn is that in this fiber bundle, you have a section with self-intersection minus m. So these are all rational surfaces. These are all different Mori fiber spaces that live in the same birational class. And so now, in higher dimension, the situation is very similar. Minimal models are no longer unique, but it's very easy to describe how to go from one to the other. And the difficulty, the more subtle thing, is to describe how 2 different Mori fiber spaces in the same birational class are connected. Yes, yes, I will. The minimal model program? Yes. No. So the minimal model program, there have been recent developments.
I know that it's recent development.
And you can have, there is a version, let's say, of the minimal model program in any dimension. It's not completely, you don't have the full minimal model as in dimension 3, but you do have enough.
But
and
it is not minimal model in this sense, yes? For n greater than 3.
It's a minimal model. It's just a variety that satisfies this. Okay, maybe let me just say.
No, yes, it is. Yes.
So, and again, you have Mori fiber spaces, and these are sort of disjoint classes. And let me just say a few words about higher dimensions. So there are, in higher dimension, things get much more complicated. And let me just mention two difficulties that appear. First of all, you have to allow for singular varieties. So it's not possible, as in the case of surfaces, to remain in this smooth universe. You have to allow some singularities, but the theory of the singularities that must be allowed in a minimal model program is very well developed, and we understand which singularities we have to accept in order to have a program like this. And the second thing is that the operations that appear here become much more complicated. So in the case of surfaces, this is just blowdowns to smooth points. But in higher dimension, you have what is similar to the blowdown, which are called the visorial contractions, but then you have some special surgeries called flips and flops that appear and that make life much harder. So let me just say, how you relate. So as I said, let me just say it for surfaces. So for surfaces, minimal models are unique, but not Mori fiber spaces. So in this case, what we have is what is called the Sarkisov program. So a Sarkisov program is an algorithm for decomposing say, let's say, a birational map between two different Mori fiber spaces. So this is a birational map, and these are Mori fiber spaces, as a composition of what is called elementary links. So into elementary links. And this holds for any dimension. So for any dimension, we have this so-called Sarkisov program. Let me tell you what are the elementary links in dimension 2. So in dimension 2, well, there are, even in higher dimensions, we have 4 types of links. So the first one, you have your P2 that is mapped fibers over a point, and then you can look at the blow up of a point. So the blow up is here's a brute surface F1, and this blow up resolves the projection from the point P. So it gives you a map to P1. So this is the first possible link. The second link is just the inverse of the first one. So you start with F1, and then you blow down the negative section to get to P2. The third one is, well, you can have F1, F0 is isomorphic to P1 cross P1, and you have here 2 different fibrations. So a Mori fiber space, part of the data is the fibration. And what this link does is just exchanges. If you're considering this fibration, now you consider this one. And this is the same thing as performing an involution here that swaps the 2 factors. And the fourth type of link which is a bit more interesting, you start with an FM that maps to P1. So here you have your fiber bundle. Then you pick a point P, you blow up this point. Then you have here you blow up this point. You get the exceptional divisor. But now you can contract the strict transform of the fiber, and you get a new P1 bundle. So now you blow up P and contract the strict transform of F, and then you get to another P1 bundle, and this is going to be Fm plus or minus 1, depending on whether this point is or not in the negative section. So these are the links, and for surfaces, any Mori fiber space can be connected by these links. In higher dimensions, the links there are also 4. There are generalization of these ones, and I'm running out of time, so let me just say that what we So first of all, there is a version of Sarkisov program for pairs x, d. And this xd is taking place of our P3 and D, but it's more general. So here, where x to y is a Mori fiber space. So let me just erase this. It's a Mori fiber space, and D is linear equivalent to minus Ks. So this is what we call a Calabi-Yau pair. So XD is called a Calabi-Yau pair. And there is a version of the Sarkisov program for volume-preserving maps between Calabi-Yau pairs into elementary links. So here, each link, all these maps that are part of the links, they are volume-preserving for appropriate choices of D. And so I run out of time, so let me, unfortunately, I cannot give you the details, but what we do in a proof, both of theorem A and theorem B, is to write, so suppose that we have a non-trivial birational map of Pn to Pn that preserves D, then it must be decomposed as elementary links in the sense of Sarkisov, and then actually we put our hands on what are the possible links that we can get. And in the case of theorem A, we show that there is no possible link. So you cannot even start your decomposition, your factorization. And in the case of theorem B, which I just erased, we actually write down precisely all the possibilities for the decomposition into Sarkisov links. And what we get, let me just quickly finish the case of theorem B, where something interesting happens. So in the case of theorem B, we had our P3 and our singular quartic hypersurface with an A1 point. We show that the only possible, the first link in the decomposition must be the blow up of P. So this gives us a structure of P1 bundle over P2. And then we keep doing the factorization. We show that it must also end with the same blow up. And then what this means is exactly that what we have here is what we call a de Jonquière map. So this can be viewed as a P1 over P2, over the function field of P2. And so any birational map of P3 that preserves D can actually be seen as an automorphism of P1 over this function field that preserves a quadric. The D becomes here a double cover of P2, and it must be preserved, or either you preserve it or you compose it with the involution that exchange the sheets, and that this is exactly that Z mod Z2 that appears. Okay, thank you for your attention.